Well, greetings, Mr. Kolazar's class. Section 5-3 is where we're starting at today, and what we're going to be looking at is the idea of light and its quantized energy, or how much energy that we can have. Now, when we look at matter, we can look at matter as it emits and absorbs light of certain frequencies and energies. And so our objectives today is going to look at how energy and frequency are related, and we're going to look at some calculations involving Planck's constant. Now, to begin with, Einstein came up with one of his first clues or ideas about explaining what he called the photoelectric effect. And back in 1905, they were looking at the idea of a polished metal surface when it was struck by a certain color of light, not how much it was, but a certain color of light, that it actually ejected or knocked particles off. And what we're looking at is the electrons from those atoms, or what we're going to refer to as the photon, or a particle of light that when it hit, it actually, or when the electron hit, actually ejected us off. And it was caused by those different colors of light, not by how much was there. Now, the photoelectric effect, as light hits a metal object, it can cause an electron to be ejected from it. Now, it depends on the type of light if this is actually going to eject. So certain frequencies of light depending on the type of material. This can actually be used to cause electricity. One example would be solar panels. Solar panels could be used there. Now, what we're going to look into is the energy of a photon. A lot of times we're just going to call it energy, but the energy of the photon is going to be equal to h, which we're going to look at as Planck's constant, and the frequency of that wave that's coming in. So it's going to be directly proportional frequency to energy. Now, Planck's constant gets us there. Now, the parts you're going to need to know, E stands for energy, and the unit is the joule. H stands for Planck's constant. It's a number 6.63 times 10 to the negative 34th joules per second. Remember, that's going to be in your gold packet, but you should know what Planck's constant is. And our last one, frequency, how many waves per second that we have, is our nu. So Einstein, we looked at light's duality in nature. It kind of looks like a wave and a particle. It has properties of both. So the photons, particles with zero mass, but it still carries energy. So energy of the photon equal to the h nu. So to look at an equation, when we look at comparing energy to frequency, so as frequency, energy or frequency increases, so does energy. Energy goes up when frequency goes up. So the frequency, the amount of waves we have per second, more waves per second, more energy. So they are going to be directly related to one another. So the direct relationship between energy and frequency. Now, if we were to look through a problem here, what is the energy of a photon from a violet portion of the sun's light if it has a frequency of 7.23 times 10 to the negative 14th per seconds? Or per seconds is the same as saying 1 per second or per seconds. So if we were to start out, what is the energy is the first problem. And then we'll look at problem number 2 in just a second. So our first step, energy is going to be equal to h nu. And so we already know that h, Planck's constant, and we also have our frequency 7.23 times 10 to the 14th. So energy is going to be equal to 6.63 times 10 to the negative 34th joules times seconds. And the other part to our equation is we have the frequency 7.23 times 10 to the 14th, and I'm going to write it per seconds. Same unit here and here. What will happen is the seconds can cancel the seconds from both parts, leaving us with just the joule. So energy, 6.63 times 10 to the negative 4, or 34th times 7.23 times 10 to the 14th comes out to about 4.79 times 10 to the negative 19th joules. And that's our unit for energy. So when we're solving for energy, the unit would be the joule. Now our second problem asks, breaking down, what is the wavelength? So this would be our problem 2. And this is just a review from last section. If we're looking for wavelength, the wavelength is equal to C over nu. And we already knew from the beginning, 7.23 times 10 to the negative 24th. So lambda is going to be equal to the speed of light is constant, 3.0 times 10 to the 8th meters per second, divided by our frequency, 7.230 times 10 to the 14th per seconds. Now when we look at this one, our units, seconds can cancel seconds, leaving us with meters. So when we go through to solve, 3.0 times 10 to the 8th divided by 7.23 times 10 to the 14th, we get about 4.15 times 10 to the negative 7th, and our units meters. So we could find out where in the spectrum we'd need to be. So this problem had two different answers that we were looking to solve for, calculating energy and then also calculating wavelength. We'll continue on with solving some problems and continuing to define the parts of our wave.